Welcome to AI for Specialists. Today we're doing a deep dive into biomimicry. The idea of learning from nature, which has had about, 3.8 billion years of R&D?
That's right, a pretty extensive testing period.
Absolutely. But here's where things get really transformative now. Artificial intelligence. It's profoundly reshaping this whole field.
It really is a fundamental shift.
So our mission today really is to unpack how AI moves biomimicry beyond just sort of copying what we see.
The observational mimicry.
Exactly. Towards decoding and actually optimizing how nature really works underneath, the functional principles. So maybe let's set the scene first. Thinking back, biomimicry has always been driven by really sharp human observation, hasn't it?
For centuries, yes. That was the only tool, really.
You think of Leonardo da Vinci, right? All those sketches of birds, trying to figure out the mechanics of flight.
Meticulous observation, trying to map form to function.
Or maybe a more direct example, Georges de Mestral, 1941. He's out walking, notices burdock burrs sticking like mad to his dog's fur.
Ah, yes, the Velcro story. Classic.
Right. Puts them under a microscope, sees these tiny hooks and loops, and bam, Velcro. It's a direct copy of a visible macroscopic form he observed.
And it's brilliant, but it's based entirely on that visible structure.
Okay, and then there's the Japanese Shinkansen bullet train, the redesign.
Yes, that's another great example of human-led insight. The original trains had this huge problem, a loud sonic boom when they exited tunnels.
Right, I remember reading about that. Annoying and inefficient.
Exactly. So the engineer, Eiji Nakatsu, he was apparently a keen bird watcher.
Ah, the nature connection again?
Precisely. He noticed how the kingfisher dives into water with almost no splash. Its beak has this incredibly streamlined shape.
Okay.
So he thought maybe that principle could work for the train. They redesigned the nose cone, mimicking the kingfisher's beak shape.
And it worked.
It worked incredibly well. Solved the sonic boom issue, plus made the train faster, and I think about 15% more energy efficient.
Wow. That's impressive. But again, it's based on observing a specific visible feature, the beak shape, and applying it.
That's the key point. These were fantastic breakthroughs, but they were often born from observing a single, usually macroscopic principle. Our human perception, it's naturally constrained, isn't it? We can only see so much. And biological systems are just immensely complex, often with hidden mechanisms we just can't perceive directly. So the process was largely about translating a visible feature into some kind of engineering equivalent.
Okay, so it sounds like human observation, even at its most brilliant, kind of hits a ceiling. There's only so far it can take you.
That's a good way to put it. You eventually run into the limits of what you can easily see and understand.
And is that where AI comes in? Is that the real game changer here?
Precisely. This is where we see that fundamental shift I mentioned. It's moving from asking, what does this look like, to how does this actually work functionally, and crucially, how can we optimize that function?
Right, getting under the hood.
Exactly. AI acts like this digital lens. It lets us see and analyze things at a scale and complexity that were just impossible before.
Can you give an example of how AI does that, like a specific method?
Sure. Let's take generative adversarial networks, GANs. You've probably heard of them creating realistic faces or art.
Yeah, they're pretty amazing.
Well, in this context, they're not just copying. They learn an entire design space. Imagine you train a GAN on, say, thousands of images of different aircraft designs and also thousands of images of sharks.
Okay, two very different things.
Right, but both highly optimized for moving through a fluid air or water. The GAN learns the underlying principles of aerodynamics and hydrodynamics from both data sets. Then it can start to generate novel designs. Sketches for aircraft, maybe, that blend features from both domains.
So not just sticking a shark fin on a plane.
No, definitely not. It might incorporate, say, the principles behind the shark's fin texture for drag reduction, but integrated into an aerodynamically sound wing shape derived from aircraft data. It's a true synthesis, creating something potentially better than either starting point in ways a human designer might never even think of.
That's fascinating. It's like AI is finding connections we just wouldn't spot.
It's pattern recognition and optimization on a massive scale.
Okay, let's bring this shift to life with maybe a really concrete case study. I'm thinking of the termite mound. That's often cited, right?
Absolutely. The termite mound is a perfect example to illustrate this difference between observation and AI-driven understanding.
So the famous human-led success story is the Eastgate Center in Harare, Zimbabwe. Designed by McPierce.
Correct. A landmark building. It famously mimicked the termite mound's apparent passive cooling system. The design used clever convective airflow, drawing in cool night air, storing it in the building mass, and venting hot air out through chimneys.
And it drastically cut energy use for air conditioning, right?
Yeah.
It was hailed as this huge biomimicry success.
It was, and it is a success based on keen observation of the mound's form and perceived function. They saw these vents and assumed a simple, passive thermosiphon effect.
But there's more to the story.
Oh, much more. This is where AI comes in and reveals a far deeper, more dynamic process. Later studies using advanced computational fluid dynamics models, basically AI-driven simulations,
Okay.
showed that the termite mound's ventilation isn't just passive. It's actually an active dynamic system driven by the daily or diurnal temperature cycles in the surrounding soil and the mound itself.
Active. How so? Not like little termite fans.
Ah, no, not fans. It's driven by physics. The temperature differences between the core, the periphery, and outside create pressure gradients. And crucially, the AI models showed that the airflow direction through the mound's intricate network of tunnels and chimneys actually reverses twice a day.
It flows backwards sometimes.
Exactly. It's an active, inverting convection cell. Air flows one way during part of the day and the opposite way during another, driven by these subtle, changing temperature differences. This incredibly nuanced mechanism optimizes gas exchange and temperature regulation far better than a simple passive chimney ever could.
And that level of detail, that dynamic reversal, that was just invisible to human observation.
Pretty much impossible to grasp just by looking at the mound or taking simple measurements. You needed the computational power of AI to model the complex heat transfer and fluid dynamics over time to see that pattern.
So AI didn't just refine the understanding, it fundamentally changed it. From static passive cooling to dynamic active ventilation.
Precisely. And that understanding allows us to think differently. We can go beyond just mimicking the form of the mound and instead try to optimize the thermodynamic function itself, maybe adapting that principle for different building types or climates in ways the original Eastgate design couldn't.
That's a really powerful illustration of the difference AI makes, going from the what to the how and why.
Exactly. Deeper function, not just visible form.
So this leads to a pretty big question then. Given AI's increasing power here, exploring designs, simulating complex systems, does the human element eventually become, well, less important, redundant even?
That's a really critical question people are asking across many fields where AI is involved.
What does that future partnership look like in biomimicry?
I think the most productive way to look at it is as a true symbiotic partnership, often called the human-in-the-loop model.
Okay, symbiotic how?
Well, AI is incredibly powerful at certain things, exploring these vast multidimensional design spaces we talked about, running thousands, millions of simulations, finding complex, non-obvious patterns in data that humans would just miss. It can generate a huge number of potential solutions or insights.
The heavy lifting of computation and pattern finding.
Exactly. But AI, at least currently, lacks genuine creativity, intuition, ethical judgment, and contextual understanding. That's where humans remain absolutely essential.
So what's our role then?
Humans are crucial for defining the right problems to solve in the first place. Asking the creative questions, the what-if questions. We're needed to curate the data that AI learns from ensuring it's high quality and relevant. And critically, we provide the judgment.
Judgment in what sense?
Evaluating the solutions AI proposes. Do they make practical sense? Are they ethical? Do they fit the broader context of the problem we're trying to solve? AI might generate a theoretically optimal design that's impossible to manufacture, or has unintended negative consequences. Humans provide that critical oversight, that reality check.
So it's not AI replacing humans, but augmenting human capabilities.
To go even further, it's more like a coevolution. AI pushes our understanding, which allows us to ask better questions, which leads to better AI models, and so on. It's about AI augmenting human creativity and intuition, allowing us to tackle problems inspired by nature at a scale and depth that was simply unimaginable before. We guide the exploration.
Guiding the exploration, I like that. So we bring the wisdom, the goals, the ethics.
And the initial spark of inspiration, often. AI provides the horsepower to explore it exhaustively.
It really feels like we're on the cusp of something significant here then. By combining our, human ingenuity and curiosity with this incredible machine intelligence,
Yes.
we can potentially accelerate the pace of innovation dramatically. It's like unlocking all that profound wisdom embedded in billions of years of nature's trial and error.
But doing it almost at the speed of thought, or at least at the speed of computation.
Yeah. Unlocking nature's secrets faster than ever before. It's quite a thought.
It is. The potential for sustainable design, for new materials, for efficient processes, It's immense.
Well, that's all the time we have today. Until next time on AI for Specialists, bye-bye.